Alright everybody, what's going on? This video we're going to look at the dot product. Alright, so far in the past videos we've added two vectors and we multiplied a vector by a scalar. So a question is, can we multiply two vectors and get a product? Okay, so one way that we can do this is we can do the dot product, and another one is the cross product, which that's in another video on its own. So let's go ahead and get started. So we got definition. We got if vector A is A1, A2, A3, vector B is B1, B2, B3, then the dot product of A and B is the number vector A dot vector B given by, so the dot product is A1 times B1 plus A2 times B2 plus A3 times B3. So we multiply the first components plus, then we multiply the second plus, then we multiply the third. And for two-dimensional vectors, it's defined in a similar way. It's just A1 times B1 plus A2 times B2. So that's the dot product. Basically, you got to know how to multiply and add. Okay. All right. So let's look at these examples here. So if we look at this first one, so that's going to give us what? 2 times 3 plus, see, 2 times 3 plus 4 times -1. And that gives us 2 as an answer. That'd be 6 plus -4 is 2. And then if we have 3 dimensions, or three-dimensional vector, this number here, that's the number 7. So let's do this. We get -1 times 6 plus 7 times 2 plus 4 times -1/2. And that is going to give us 6 as an answer. And then this one, same thing. So remember, this is 1, 2, -3. This is like the vector 1, 2, -3. And this one would be what? 0, 3, -1. Okay, but I mean, you don't have to write this out. I'm just showing you this vector is this one, this vector is this. So if we multiply, we get 1 times, whoop, I was fixing to multiply the 1 times that 2 there. See, there's no I term, that's 0. And then plus 2 times 2. And then we get plus -3 times -1. -3 times -1. And that would give us 7 as an answer. All right. So let's look at this, properties of the dot product. So if vectors A, B, and C are vectors in V3 and C is a scalar, then the dot product of A dot A is just the magnitude of A squared. This right here shows that doesn't matter what order you do the dot product in. This one just saying we can distribute. This one you can multiply the scalar. C is the scalar here. Now keep in mind we've got a scalar C and we've got a vector C. So this C doesn't have a arrow over it, so that's the scalar. So we can multiply the scalar to A and then do the dot product of that with B, or we can do the dot product and then multiply the scalar, or we can do the scalar times B and then do the dot product of A and that. And then the 0 vector times a vector A is equal to 0. So let's just, for this one, let's prove property 1 and 3. Okay. So this will be the proof of the first one. Okay. So we want to do vector A dot vector A is equal to. Now, keep in mind when you're looking at these vectors, and it's saying they're all vectors in V3. So you've got to understand that vector A, that's going to be A1, A2, A3, and we're doing the dot product with itself. You see that? And so if we do the dot product, we got A1 times A1 is A1 squared, plus A2 times A2, that's A2 squared, plus A3 times A3 is A3 squared. All right, so it's saying that's the magnitude of A squared. Well, think about this. You remember in the previous lesson that this was the magnitude of A, right? So we have this, we don't have the square root. So if we square that, then the square root's gone, and so you can see that would be the magnitude of A squared. Okay? And so now let's prove 3. So this is the proof of the second one. Not the second one, but the third one. So I've got A dot vector B plus vector C. And I want to show that it equals vector A dot vector B plus vector A dot vector C. That's what I'm going to show. So let's write this out. So this is going to be vector A is A1, A2. Whoop, I don't know why I put a plus. There's vector A. And then vector B plus vector C, that's going to be what? That's going to be B1 plus C1, right? We see this is B1, B2, B3. This is C1, C2, C3. So we're going to add the components. And so then that's B2 plus C2. And then this is going to be B3 plus C3. All right. So now let's do the dot product of this. And so this is going to be A1 times B1 plus C1, right? We got to do this times this, plus this times this, plus this times this. All right. So that's going to be plus A2 times B2 plus C2 plus A3 times B3 plus C3. And now what am I going to do? Well, now I'm going to distribute the A1, distribute the A2, distribute A3. And so that's going to be A1 B1 plus A1 C1 plus A2 B2 plus A2 C2 plus A3 B3 plus A3 C3. All right. So now let's get all the AB terms together, and let's get all the AC terms together. All right, so this is going to be A1 B1 plus, and then A2 B2 plus A3 B3. Okay, so there's that one. And then plus, and then let's do A1 C1 plus A2 C2 plus A3 C3. Okay, because it doesn't matter what order we add them in, right? That doesn't matter. See, that's from where is that? I had it somewhere. I think that was in the last lesson where it's commutative when you add. I think that was the last lesson. But look at this. Isn't this just the dot product of A and B? You see that? See, I would do A1 times B1 plus A2 times B2 plus A3 times B3. right there. And then plus, and then this is just the dot product of A and C. And so you can see there, that gives you this right-hand side. So, you know, there you have it. And you can, you know, if you're bored or something sitting around, you can prove the other ones. All right, so let's look at this one. So it says theta is the angle between the line segments OA and OB. Okay, so we've got OA and OB. Here's theta. Note that if vector A and vector B are parallel vectors, then theta equals 0 or theta equals pi. Okay, I'll talk about that in a little bit. We'll get a little more into that later. But if theta is 0 or pi, then the vectors are parallel. Okay, which that makes sense. If the angle between the vectors is 0, then you know they're parallel. Or if it's pi, that's 180, and we'll talk about that, how they're parallel, but they are going in opposite directions. But like I said, I'll talk about that in a minute. So if theta is the angle between the vectors A and B, then A dot B is equal to the magnitude of A times the magnitude of B times cosine theta. Okay, so that's one way that we can get, you'll see we'll be able to get the angle between two vectors using this, a little bit different form of it, but we'll be able to find theta. But we can also use this to find the dot product. So let's look at this. So before when we were finding the dot product, what did they give us? We got what? See, they gave us the vectors. Okay, we had the components of the vectors, and so we could do the dot product. But what happens if they give us the length of the vector and the angle between them? Okay, that's what we're given, the length of each vector and the angle between the vectors. Well, it's the magnitude, that's the lengths, times the cosine of the angle between them. And so in this case, we have A dot B is equal to the magnitude of A. So 4 is the magnitude of A, and 6 is the magnitude of B. And so that's going to be 4 times 6 times the cosine of pi over 3. And so that's going to be 4 times 6 times, and then what's the cosine of pi over 3? That's 1/2. And so we would get 12. That's the dot product of those two vectors. Okay. And so basically what we have here is you have a vector. You've got vector B with length 6. And then here you got vector A with length 4. And then this angle here is pi over 3. So the dot product, that's 12. All right, so here we have a corollary. If theta is the angle between the non-zero vectors A and B, then cosine theta is the dot product of A and B over the magnitude of A times the magnitude of B. All right, so you can see this comes from this right here. It's just both sides are divided by the magnitude of A times the magnitude of B, which comes under here. We just solved this for cosine theta. All right, so what this allows us to do is it allows us to find the angle between two vectors. So here we want to find the angle between the vectors A and B. All right, so what do we need to do to find that? Well, we need the dot product and we need the magnitude of each vector, don't we? So let's find it, see, and then we can use this. So let's just find the magnitude of A. So the magnitude of A is equal to, remember, the square root of 2 squared plus 2 squared plus negative 1 squared. Okay, this, we've already done this. Okay, this was done in the last video when the section on vectors. So it's just this squared plus this squared plus this squared. And that ends up giving us 3. And then we've got the magnitude of b. That's going to be 5 squared plus negative 3 squared plus 2 squared. It's the square root of that. And that equals the square root of 38. All right, so you can see we've got this and we've got this. Now we need the dot product. So the dot product is equal to, let's just write this out. Let's write the vectors out so you can see it good. I'm sure this isn't very difficult for you, but let's do it anyway. There might be some people watching, well, I don't understand. So that's going to be 2 times 5 plus 2 times plus 2 times negative 3 plus negative 1 times 2. Let's see, 2, 5, 2, negative 3, and negative 1, 2. Just making sure I had everything written down right. And that equals 2. And so now we just plug everything in. So cosine theta is equal to 2 over 3 times the square root of 38. See, I just replaced this with 2. I replaced the magnitude of a with 3 and replaced the magnitude of b with square root of 38. So what does this tell us? Well, this tells us that theta is what? The inverse cosine of 2 over 3 square root of 38. So when I punch that into my calculator, I get 84 degrees is the angle between those two vectors. Okay? And so, well, I'm not gonna draw it. You can draw it out and you can see that it'll be about 84 degrees. You know, try to draw it to where, you know, the scale is pretty close. So, all right. All right, so let's look at this. It says 2 non-zero vectors A and B are called perpendicular or orthogonal. Perpendicular or orthogonal if the angle between them is pi over 2. Okay, so think about that for a minute. So if the angle between two vectors is pi over 2, 90 degrees, yeah, they're perpendicular, right? So let's look at this. Let's plug that into this formula for the dot product that we had up there earlier. Okay, so it doesn't matter what the magnitudes of A and B are. Just know that we've got A dot B is the magnitude of A times the magnitude of B times the cosine of pi over 2. Well, what's the cosine of pi over 2? It's 0. So 0 times this, doesn't matter what it is 0. Oh, so that tells us if the dot product of two vectors is 0, then that means those two vectors are orthogonal. And conversely, if A dot B is 0, well, just what I said, if A dot B is 0, then cosine theta is equal to 0. So theta is equal to pi over 2. All right? So the 0 vector is considered to be perpendicular to all vectors. All right? And then here we have it. Two vectors A and B are orthogonal if and only if A dot B is 0. And I know it may not look like it, but that's a dot. That's not a minus sign. That is a dot. Okay? All right, so let's look at this example. So it says determine whether the given vectors are orthogonal, parallel, or neither. Okay, so we know how to determine if they're orthogonal, right? The dot product is 0. But we didn't really talk about if they're parallel. How to know if they're parallel. Well, you can write this down. I'll say it a couple of times. It says, okay, so two vectors are parallel if they are scalar multiples of one another. So if they're scalar multiples of one another, then the two vectors are parallel. And I'll show you what I mean by that. And I think what I want to do, I know I've got this right here, problem 1, problem 2, and this one's problem 3. But I think I'm going to start with this one first, because I think I'll be able to explain the parallel and stuff better if I start with this one. This one, let's see, this one first. All right, so let's check real quick to see if they're orthogonal. Okay, that's the easiest thing to check. So if I take A dot B, then that's equal to 4 times 3 plus 5 times negative 1 plus negative 2 times 5. And what does that equal? That's 12, and that's negative 10. So that's going to be 12 plus negative 10 is 2, and 2 plus negative 5 is negative 3. So that tells us they're not orthogonal. Okay, so let's see, is there a way to write these as scalar multiples of one another? So let's take this vector right here. All right, so is there something that we can factor out of this vector and this vector, like a scalar? Can we factor a scalar out of either one of those? Well, this doesn't have a common factor that we can factor out, does it? And this one doesn't either. Okay, so we cannot write these as scalar multiples of one another. Okay, and so this would be neither. Okay, so, and if that doesn't make sense, let's keep working these. Okay, so that's neither. Okay, so I'm sure you understand the dot product, not 0, so that tells us it's not orthogonal. So, but what I explained there with the parallel, that might not quite register with some of you. Okay, and if it doesn't right now, that's fine. Okay, but I'm going to show you in a minute. Okay, so let's go back up here to 1. So let's find the dot product here. Let's just check to see if it's orthogonal. So A dot B is equal to what? 3 times 5 plus negative 1 times 9 plus 3 times negative 2. And so that's going to be 15. Let's see, that's going to be 15 minus 9 minus 6. And so that gives us 0. So these are orthogonal. Okay, we can stop there. Once we get that dot product as 0, we can just stop. All right, now let's look at this third one. So real quick, we'll check the dot product, which it's not going to be 0. I already know the answer. So that's going to be negative 8 times 6 plus 12 times negative 9 plus 4 times negative 3. And that equals negative 168. So they're not orthogonal. So let's look and see, are they parallel? So if they're not orthogonal, if they're not parallel, then they're neither, right? So let's look at vector A. So vector A, Notice how I have a common factor of 4. So I could factor out a 4, but look at this. Just bear with me for a second. If I factor out a 4, that's fine and everything. That would give me -2 plus 3 plus 1k. But notice over here in this problem how there's a negative in front of the I, and then see how the signs are opposite? So instead of factoring out a 4, how about I factor out a -4 so I'll have the same signs as this one does. So when I do that, that's going to leave me with 2i plus 3j plus k. And then for vector b, well, can I factor something out? Yeah, I can factor out a 3. Well, I'm sorry. That's not plus, is it? I just sat there and talked about changing the signs, and I put plus anyway. Those should be minuses. Changes the sign. And that right there just goes to show you pay attention to what you're doing. All right, so I get 2i minus 3j minus k. And see these vectors, they're scalar multiples. So that tells me that they are parallel. And so that's how you check to see if it's parallel, orthogonal, or neither. Okay? All right, so let's continue on. Okay, so this is where I was going to talk about more about, when we talked about the vectors being parallel and that kind of stuff. So look at this. So if I take the dot product can tell us quite a bit about the about two vectors. So if the dot product is positive, then vectors A and B point in the same general direction. Okay, so, and I'm going to explain in a minute what we mean by the same general direction. And theta is an acute angle. That means it's what? It's between 0 and 90 degrees. If the dot product is 0, well, we already know that means they're perpendicular. And then if the dot product is less than 0, then what? Vectors A and B point in generally opposite directions, and theta is an obtuse angle. It would be an angle between 90 and 180. Okay, and just think about that for a second. Let's just go back up here to, where was it? Right here, this right here. So think about this. These magnitudes down here, they're going to be positive, right? When you find the magnitude of a vector, that's positive. So this denominator is going to always be positive. So look at this. If the dot product is positive, then when I take the inverse cosine, that's going to give me an angle in the first quadrant. Remember from trig that whenever you do the inverse cosine of a number, theta is going to be between what? 0 and pi. Remember, sine, when you do sine, theta is between -pi/2 and pi/2, right? So if this is positive, then your angle is going to be in the first quadrant between 0 and 90. But if this is negative, then you're doing the inverse cosine of a negative number. Well, here we go. Cosine's negative in the second quadrant. It's going to be between pi/2 and pi. All right. So hopefully that helped you seeing that. All right. So up here, when it was positive, when it was negative, the dot product, we talked about when it's positive, it points in the same general direction. And then when it's negative, it points in generally opposite directions. Okay, so now listen to this. A and B, and that should have an arrow over it. Vectors A and B point in exactly the the same direction if theta equals 0. So that would mean cosine theta is equal to 1. Okay? And the dot product of A and B would be the magnitude of A times the magnitude of B. And that just goes back up to earlier. Okay, if cosine theta is 1, look at this. Where is it? So if cosine theta is 1 and we bring this up 1 times this, we would just have the magnitude of A times magnitude of B is equal to the dot product of A and B. That's with cosine theta being 1. All right. So that's when they point in exactly the same direction. And then A and B point in exactly opposite directions. Okay, they would still be parallel, but just going in opposite directions. Theta is equal to pi. So that means cosine theta would be what? -1. See that? See, if you have two vectors, one going this way, one going this way, that angle there is pi. They're going in exactly opposite directions. And that would give us the dot product of A and B is equal to negative magnitude of A times magnitude of B. Okay? So I hope you can see that. Okay? All right, so now let's talk about direction angles. The direction angles of a non-zero vector A are the angles alpha, beta, and gamma. I know the gamma I draw might not look that good, but it's gamma. In the interval 0, and I have no idea why I put a degree symbol on that 0, is in the interval 0 to pi that vector A makes with the positive x, y, and z axes. The cosines of these direction angles, cosine alpha, cosine beta, cosine gamma, are called direction cosines of vector A. Okay, called direction cosines. All right, so let's look at a picture. So here I have vector A, okay, and you can see alpha, that's the angle it makes with the positive x-axis. Angle B, that's the angle it makes with the positive y-axis. And angle gamma, that's the angle it makes with the positive z-axis. All right, so let's look at this. So what is the angle between vector A and alpha? I'm sorry, and the x-axis. Okay. What would that be? All right. Well, that is equal to what? That's going to be cosine alpha is equal to what? Vector A, right? Vector A, we need the dot product of A and what? Well, here we have the vector I, right? That's along the positive x-axis. Okay, so basically we can look at finding the angle between A and I. Okay, and that angle would be the same no matter if this was, 5 times vector I. Okay, it doesn't matter. Let's just use I. And so it's the dot product of those two, and that's over the magnitude of A times the magnitude of I. Okay? And one thing I want to say here is this vector. See if I can get this back on there. All right. Well, one thing I want to say here, this length vector A, okay, we're going to call that, well, I mean, I don't know. I'm sorry. I don't need to call it anything. I just want you to understand that the dot product here is what? A1, right? So think about this. Vector A is A1, A2, A3. And I'm going to do the dot product with this. So it's A1 times 1 is A1 plus A2 times 0 plus A3 times 0, which is A1, over, and what's the magnitude of I? Remember, that's the magnitude of this vector right here. That's 1 squared plus 0 squared plus 0 squared. Square root of that, that's 1. So 1 times the magnitude of A is just the magnitude of A. All right? And so that gives us cosine alpha is equal to A1 over the magnitude of A. And then cosine beta, and you do that in a similar way. You just, for beta, you would use vector J. Okay? That would be what? A2 over the magnitude of A. And then cosine gamma, you could do that in a similar way. Instead of I, you would have vector K. That is equal to A3 over the magnitude of A. Okay? All right, so that's that right there. Okay, and let me take this, and I'm going to see if I can't. I'm going to bring this down some. All right, so hopefully that made sense. Now, what's another thing that we could say about this? Well, this also, we know that cosine squared alpha plus cosine squared beta plus cosine squared gamma is equal to 1. Now, how in the world do we know that? Well, let's look at it. Let's take the right-hand sides. So if I have A1 over the magnitude of A squared plus A2 over the magnitude of A squared plus A3 over the magnitude of A squared. So let's say I have that. That's going to give me A1 squared over the magnitude of A squared plus A2 squared over the magnitude of A squared plus A3 squared over the magnitude of A squared, which that's going to give me what? A1 squared plus A2 squared plus A3 squared over the magnitude of A squared, right? So far, so good. Well, remember, the square root, I'm going to erase this, but the square root of that is what? Is the magnitude of A, right? This is the magnitude of A. But if I square it, see, this right here is the magnitude squared. Because remember, the magnitude of the vector is A1 squared plus A2 squared plus A3 squared, the square root of that. But we don't have the square root. And so this is the magnitude of A squared, that's the numerator, over the magnitude of A squared, which equals 1. Okay? All right, so I hope that makes sense. All right, so I'm going to erase this because I want to. You can rewind it and copy it down if you want to, but rewind the video and copy it down. But so let's look at this. So let's look at a way that we could write vector A. All right, so we know vector A. If we have vector A is A1, A2, A3, right? That's vector A. And so this is also equal to what? The magnitude of A times cosine alpha. So I replaced A1. Well, what's A1? Well, if I multiply this up, that's this. And then A2, that's going to be the magnitude of A times cosine beta. And then A3 would be what? The magnitude of A times cosine gamma. All right. So what if I factor out that magnitude of A? That's a scalar. I can factor that out, right? And so the magnitude of A times cosine alpha, cosine beta, cosine gamma. And that's vector A is equal to that, right? So what now? Well, let's divide both sides by the magnitude of A. So that's going to give me 1 over the magnitude of A times vector A is equal to cosine alpha, cosine beta, cosine gamma. All right, so let me ask you that. What does that tell us? So that says the direction cosine of A are the components of the unit vector in the direction A. All right. This says that the direction cosines of A are the components of the unit vector in the direction of A. Remember, I think we talked a little bit about we talked some about unit vectors in the last video. Okay. All right, so let's look at this next example. It says find the direction angles of the vector. Okay, so let's look at this. See, this is what we were talking about earlier, the direction angles of a vector. Okay, that's the alpha, beta, gamma. All right, so let's find the direction angle. So what I'm going to do here is, since it's easy, let's grab this and let's copy it and let's put it right here. All right, so let's see what we've got. All right, so what do we need? All right, we need the magnitude of A. I mean, we already know what A1 is. It's 1. A2 is 2. A3 is 3. So we just need the magnitude of A. So the magnitude of A is equal to the square root of 1 squared plus 2 squared plus 3 squared, and that is equal to the square root of 14. And so there you have it. So we've got cosine alpha is equal to what? 1 over the square root of 14, which that means alpha is the inverse cosine of 1 over square root of 14. And so that's going to be about 74 degrees. And then we've got cosine beta is A2, which is 2 over the magnitude of A, which that tells us beta is equal to the inverse cosine of 2 over square root of 14. Punch that in your calculator, we get 58 degrees. And then we have cosine gamma is A3, which is 3. See, remember this is A1, A2, A3. That's 3 over the square root of 14, which that tells us gamma is equal to inverse cosine of 3 over the square root of 14. So that tells us gamma is it 37 degrees? No. And so there you have it. Okay. All right, let's move on. Scalar and vector projections. All right, so scalar projection of B onto A and vector projection of B onto A is this. So the scalar projection of B onto A is, this is the notation for it. This is the scalar projection of B onto A is A dot B over the magnitude of A. And the vector projection of B onto A is, it's the magnitude of A dot B over the magnitude of A. It's the dot product of vector A and B over the magnitude of A squared times vector A. Okay. So let's talk about this just a little bit. So if you have two vectors, okay, say vectors A and B with the same initial point, and we want to talk about the vector projection. And let's just look at while I'm telling that, let's look at the pictures. So this would be the vector projection right here. See, we've got two angles, A and B. So the vector projection is this vector right here. You think of it like if you're standing here and you're shining let me not draw an arrow. Let's say you've got you're shining the light down, and then that shadow it would make, that's your vector projection. Okay. And the scalar projection, which also called component of B along A, so the scalar projection of B onto A also can be called the component of B along A. That's defined to be the sine magnitude of the vector projection. So that's the magnitude of the vector projection. And here's an example that this one and this one that's the examples of vector projection. And this one is an example of the scalar projection. Okay, so we've got a vector here, and this is just the length here. All right, the magnitude. All right, so let's do some example. Let's do an example of finding that. So hopefully you understand what that is. So the vector projection, that's going to actually give you a vector. That's going to give you what that vector is. And then the scalar is going to give you the magnitude. All right, so find the scalar projection and vector projection of B onto A. Okay. All right, so let's write our formulas down. So here's the scalar. Okay, the scalar, that's going to be B onto A is equal to the dot product of A and B over the magnitude of A. And then the vector projection, that's going to be the vector projection of B onto A. That is going to be the dot product of A and B over the magnitude of A squared times vector A. All right. All right, so let's look at this. What all do we need? What do we need for our formulas? Well, we need the dot product, right? We need the dot product of A and B, and we need the magnitude of A. All right. So let's come up here. Let's do the dot product of A and B. So that's going to be -2 times 1, -2 times 1, plus 3 times 1, plus 3 times 1, plus 1 times 2, plus 1 times 2. And so that ends up being 3. And then we need the magnitude of A. So that's going to be what? That's the magnitude of this one. So that's going to be -2 squared plus 3 squared plus 1 squared. And it's the square root of all that. And that ends up being the square root of 14. All right. And so now we're ready to find it, right? So let's find the scalar projection. So we've got the scalar projection of B onto A is equal to the dot product. I'm doing this one, the scalar, the dot product, which is 3 over the magnitude of A, which is square root of 14. And there's your answer. Some tough stuff, isn't it? How about that? And now let's do the vector projection. So the vector projection of B onto A is equal to the dot product, which is 3, over the magnitude squared, so that's the square root of 14 squared, times vector what? Times vector A. And what's vector A? That's -2, 3, 1. And so that's going to be 3 over 14 times vector A. Okay, times vector. I don't know what happened. I was right in the middle of recording and my OneNote just rebooted. So I'm back. All right, times vector A, which is 2, 3, 1. And so this is equal to 3 over 14, -2, 3, 1. And so that is going to end up giving me -7 over 3, 9 over 14, and 3 over 14. I just multiplied this vector times the scalar, 3 over 14. And there's your vector projection. Okay. All right, believe it or not, we are actually almost done here. We've got this to look at and two more examples, and we will be finished. I know you're happy. All right. All right, so suppose the constant force is a vector. Vector F is equal to vector PR pointing in some other direction. If the force moves the object from P to Q, then the displacement vector is vector D equals PQ. The work done by this force is defined to be the product of the component of the force along D and the direction moved. So work is the magnitude of F times cosine theta times the magnitude of D. But I mean, we can write this as W is equal to the magnitude of F times the magnitude of D times cosine theta. Okay, just move it around like that. All right, and then what is that? Does that look familiar? Remember when we had the magnitude of A times the magnitude of B times cosine theta? Remember that? That was vector A, the dot product of vector A and B, right? So the work, that would be the dot product of F and D. All right. So this is a little bit different probably than what you've been used to. So when we talk about work, all right. So if if you're at this point, you've had all the other stuff in calculus. So there's a section in calculus on work where the work it was defined, the work done by a constant force F in moving an object through a distance d as W work equals force times distance. But this only applies when the force is directed along the line of motion of the object. Okay, so the force was going along that line of motion. All right, but here, notice what it says. Suppose the constant force is a vector pointing in some other direction. And I think, yeah, I got a drawing of it. So it's like this. See, here's the direction that we're going. Okay, here's the direction, but the force is coming at an angle here. Okay, so we've got this right here. Okay, so let's look at it. So you've got the work is magnitude of the force times cosine theta times the magnitude of D, which we just wrote it, magnitude of F times magnitude of D times cosine theta, which is just the dot product of F and D. That's all it is. All right, so let's look at this. So we have a wagon is pulled a distance of 100 meters along a horizontal path by a constant force of 70 newtons. The handle of the wagon is held at an angle of 35 degrees above the horizontal. Find the work done by the force. All right, so let's look at it. So let me draw my wagon. So there we have a wagon. It's got a handle on it, right? And the wagon is moving in this direction. All right, so this is the direction that it's moving in. There's the force, and the angle between them is 35 degrees. So what that's going to look like if I take this angle and bring it over here, there's my force. There's the vector D, and then this is theta, which, well, we'll call that, there's your 35 degrees. So I know work is equal to what? It's the dot product of the force and the distance, right? And it's the dot product of the force and the distance. Or the displacement vector. All right, so let's see. Well, look at that. They don't give us what vector F and vector D are, do they? They don't give us the vectors. They give us the magnitudes, right? They give us the magnitude. So we can use this. See, the magnitude of F and D, and we know the angle between the vectors. So see, we've got the magnitudes. So this is equal to the magnitude of F times the magnitude of d times cosine theta. So that's going to be the magnitude of F, which says a constant force of 70 newtons. So that's 70 times the magnitude of D, which is a distance of 100 meters. So that's 100 times the cosine of the angle between them, which is 35 degrees. And punch all that into your calculator, you get 5,734, and that's newtons and meters, right? Meters. And so that would be Newton meters, or we can say 5,734 what? Joules. All right, so there's that problem. So now let's look at this next one. It says a force is given by a vector F, there's vector F, and moves a particle from the point, okay, so it's moving from the point P to Q. Find the work done. All right, so we know that the work is the dot product of the force and displacement, distance. All right, so they give us F, and we need to know what D is. Well, vector D is equal to vector PQ, right? That's equal to vector PQ. Now, how do we find that? Well, do you remember? I believe we did this in the last video. That's going to be 4 minus 2, 4 minus 2, 6 minus 1, and 2 minus 0. And so vector D is 2, 5, 2. So look at that. I've got vector F, I've got vector D. Now all I have to do is find the dot product. So W is equal to F dot D. And so I'm going to go ahead and put it in this form. So I'm going to rewrite this into this form. That's 3, 4, 5 dot 2, 5, 2. And so that is equal to 3 times 2 plus 4 times 5 plus 5 times 2. And that ends up being, what's that? Is that 36? Yeah, 36. And, you know, they don't give us units on this one. But if the length was in meters and the force in newtons, then that would be 36 joules. I know they don't give us that, but let's just say they did. Okay. All right, so there you have it. That's the lesson on dot product. So hopefully it all made sense. Hope you enjoyed it. Hope you didn't fall asleep. But I appreciate you watching. Check out my other videos. Give me a like, share, and subscribe. And I will see y'all in the next one. Later.